Welcome to the video lecture for section 3.1. My name is Jorge Young and this is for MAC 1105. So the objectives for 3.1, we're going to determine whether a relation represents a function. We're going to find the value of a function. We're going to find the difference quotient of a function. We're also going to find the domain of a function defined by an equation. And we're also going to form the sum, difference, product, and quotient of two functions. So the first thing is determine whether a relation represents a function. So here, y is equal to 3x minus 1 is a function, and you're going to see why it is a function. There are some things that we can do in order to determine whether an equation is a function or not. And so here's another example. This is a number of representatives. And the number one thing about a function, if you can't look at the graph, is to see whether or not the inputs are related to only one unique output. So in this case, the state will be the output and the number of representative would be the output. And so, if an input is associated with simply one unique output, then the answer that it is a function. And then here you can see that person and phone number. And so this does not this relation does not represent a function because Colleen is actually connected to two different telephone numbers. And this one here, animal life expectancy. So this is a function because each animal is only related to just one value for life expectancy. And so the definition of a function is the following. Let x and y be two non-empty sets. A function from x to y and to y is a relation that associates each element of x with exactly one element of y. And so this is what this looks like. And so we've already done domain and range. And so the easiest definition of a function would be that we take an element from the domain and we map it to an element in the range. Now, this mapping has to be unique. And in other words, an element in the set of the domain values cannot be associated with two distinct values in the range. And so here's some examples. We're going to determine whether a relation is a function. So for each function, state the domain and range, then determine whether the relation is a function. So we have A, B, and C. So we have the set A contains the ordered pairs 1, 4, 2, 5, 3, 6, 4, 7. B is the set that contains the ordered pairs 1, 4, 2, 4, 3, 5, 6, 10. And then C contains negative 3, 9, negative 2, 4, 0, 0, 1, 1, and negative 3, 8. So for the first one, the domain of this relation is 1, 2, 3, 4. Those are the inputs. The range is 4, 5, 6, 7. This is the output. So this relation is a function because there are no ordered pairs with the same first element and different second element. In other words, each element in the set of the domain is mapped to just one unique element in the range. Now, letter B. The domain of this relation is 1, 2, 3, 6. Its range is 4, 5, 10. This relation is a function because there are no ordered pairs with the same first element and different second elements. Now, for letter C, the domain of this relation is negative 3, negative 2, 0, 1. The range is 0, 1, 4, 8, 9. This relation is not a function because there are two ordered pairs, negative 3, 9, and negative 3, 8, that have the same element with different second elements. So again, here we're going to determine whether an equation is a function. So we have the equation x squared plus y squared is equal to 1 defines y as a function of x. And so to determine whether the equation defines, this equation actually defines a unit circle. Is it a function? We're going to solve the equation for y. And then we see for values of x for which x is between negative 1 and 1, two values of y are going to result. For example, if x is equal to 0, then y is equal to plus or minus 1. So two different outputs result from the same input. This means that the equation x squared plus y squared is equal to 1 does not define a function. So the next thing we're going to do is find a value of a function. And so here we have A, B, C, and D. So in A, our domain involves 1, negative 1, 0, square root of 2. The function is f of x is equal to x squared. So what's going to happen is, the rule here is we're going to take the element from the domain and we're going to square it to get the output or an element in the range. So if x is 1 and f of x is x squared, then f of 1 is equal to f of negative 1. Which means that it's equal to 1 because we took the 1 and the negative 1 and we squared it. And then the second one, we take the 0, we square the 0, we get 0. And then square root of 2, when we square that, we get 2. And so here you can see that although we have two distinct values of the x that map into one value, this is still a function. So in other words, the values of the elements of the range can repeat. Here for letter B, we have f of x is equal to 1 over x. The domain, -2, -1, 4. And so when we map each of these values into the range, we get for -2, we get -1/2. For -1, we get -1. And for 4, we get 1/4. And then for letter C, x maps to g of x, and g of x is a square root of x. And then you see the domain of x is 0, 1, 2, and 4. And then the range of x here turns out to be 0, 1, square root of 2, and 2. Again, this is a function because it maps each unique element. Here it's mapping to one unique element. And then for letter D, x maps to g of x, which is equal to 3. And so the domain is 0, -2, 3, and they all map to 3 because this is a constant function. So the next thing we're going to do is find values of a function. So for the function f defined by f of x is equal to 2x squared minus 3x, evaluate the following. So we have a, b, c, d, e, f, and g, and we're going to go ahead and evaluate those. So for a, we're going to substitute 3 and x for the equation. So f of x then becomes f of 3, which becomes 2 times 3 squared minus 3 times 3, which is equal to 9. So the image of 3 is 9. In other words, the output is 9 if the input is 3. For b, f of x plus f of 3, then we get 2x squared minus 3x plus 9, because we know that f of 3 is equal to 9, so we can substitute it. And so therefore we get 2x squared minus 3x plus 9. And then for c, we're going to multiply the equation for f by 3. So we have 3 times f of x. And so you can see here that we simply multiply f of x by 3, and we end up with 6x squared minus 9x. And then for d, we're going to substitute negative x for x in the equation for the function and simplify. And so f of negative x then becomes 2x squared plus 3x. And then also be careful with the use of parentheses. If you have a negative value and you're squaring anything, or you have an exponent, you want to put that negative within parentheses. For e, negative f of x, you can see that we end up with negative 2x squared plus 3x. For f, we're going to substitute 3x for x in the equation, and then we're going to go ahead and simplify. So f of 3x is equal to 18x squared minus 9x. And then for g, we're going to substitute x plus 3 for x in the equation and simplify. So f of x plus 3 is equal to, 2 times x plus 3 squared minus 3 times x plus 3. So remember, it does not matter what you have within these parentheses. You can have f of anything, and all you're doing is replacing the variable with the value that you have, or the expression that you have within the parentheses here. And so this is the same thing. If this would have been f of 1, you simply replace x with 1 and you simplify. And so the same thing here. Here you have x plus 3, so you replace every single instance of x with x plus 3, and then you simplify. The next day we're going to find the difference of a quotient of a function. So the difference quotient of a function f at x is given by f of x plus h minus f of x over h when h does not equal 0. For those of you who are going to move on to calculus, this is going to become familiar. So we're going to find the difference quotient of a function. So we're going to find the difference quotient of each function. We have a, which is f of x is equal to 2x squared minus 3x. B, f of x is equal to 4 over x. And c, f of x is equal to the square root of x. So the first one, we're going to replace, we have f of x plus h. So we go ahead and we take f of x and we rewrite it as f of x plus h. So you can see here in red what they did. And then this second part is just minus f of x, which is just whatever the function is. And then in this case here, what we're going to do is we're going to multiply everything out within the brackets. And that's what they did in this second step. And then they got rid of these brackets, which means the signs change in the second function. And then you start combining, you multiply out the 2, and you start combining like terms. And then here, the next to last step, you can factor out an h. And so the difference quotient for this particular function is 4x plus 2h minus 3. Here we have letter B again, f of x plus h minus f of x over h. So here we have 4 over x plus h minus 4 over x over h. And then so what we do is we start combining. We're going to multiply this function by x plus h, and then this one here by x allows us to combine it into one fraction. And then we start combining like terms. And here we end up with negative 4h times x plus over x times x plus h times h. we're going to factor out an h, and so we end up with negative 4 over x times x plus h. The next one, f of x plus h minus f of x over h, where f of x is the square root of x. Again, you see, we go ahead and substitute the value of x plus h for x. And then in order to get rid of the radical, we multiply by the conjugate. So we multiply the numerator and denominator by the conjugate. So we're going to rationalize the numerator. And then by doing that here, we end up with this little trick right here. We've already gone over this several times. So our numerator then just simply simplifies to h. And then the next to last step, actually the last step is when you just divide out the h. So we end up with 1 over square root of x plus h plus the square root of x. Next thing is we're going to find the domain of a function defined by an equation. So we're going to find the domain of each one of these functions. So for a, which we have x squared plus 5x, the function says to square the number, then add 5 times the number. Since these operations can be performed on any real number, the domain of f is a set of real numbers. Another thing is that this is a polynomial function, so therefore is defined for all real numbers. The next one is b, which is 3x over x squared minus 4. So the function g says to divide 3x by x squared minus 4. Since division by 0 is not defined, the denominator can never be 0. So x can never be equal to negative 2 or 2. So the domain of this function g is x such that x does not equal negative 2 and x does not equal 2. So it's all real numbers except these two values. And then c, the function h says to take the square root of 4 minus 3t, but only non-negative numbers have real square roots, so the expression under the square root, the radicand, must be non-negative, greater than or equal to 0. So this requires the radicand to be greater than or equal to 0. And when we solve that, we get that t is less than 4/3. So the domain of h is all numbers t such that t is less than or equal to 4/3, or in interval notation, it's negative infinity 4/3. And then the function for d, the function f says to take the square root of 3x plus 2 and divide this result by x minus 5. This requires that 3x plus 2 is greater than or equal to 0. So x has to be greater than or equal to negative 4, and also that x minus 5 does not equal 0. So x cannot equal 5. Combining these two restrictions, the domain of f then become all numbers x such that x is greater than or equal to negative 4 and x does not equal 5. So finding the domain of a function, start with the domain as a set of real numbers. If the equation has a denominator, exclude any numbers that give a 0 denominator. If the equation has a radical of even index, exclude any numbers that cause the expression inside the radical, which is known as the radicand, to be negative. Now, next thing is we're going to form the sum, difference, and product and quotient of two functions. So if f and g are functions, the sum f plus g is the function defined by f plus g of x, f of x plus g of x. The difference, again, f minus g of x is equal to f of x minus g of x. The product, f times g of x, is equal to f of x times g of x. And then the quotient, f divided by g of x, is f of x divided by g of x as long as g of x does not equal 0. So here, let f and g be two functions defined as follows. So f of x is equal to 1 over x plus 2. G of x is equal to x over x minus 1. So we're going to find the following functions and determine the domain in each case. So for the first one, we're simply adding the two functions. So then we end up with x squared plus 3x minus 1 over x plus 2 times x minus 1. Now, the domain of f plus g consists of those numbers and x that are in domains of both f and g. So therefore, the domain of f plus g is all numbers x such that x does not equal negative 2 and x does not equal 1. The next one is the difference. So we're just going to do 1 over x plus 2 minus x over x minus 1. Combine both of them, so we get negative x squared plus x plus 1 divided by x plus 2 times x minus 1. So the domain of the difference of these two functions, again, is all numbers x such that x does not equal negative 2 and x does not equal 1. For c, the product of the two functions, again, domain, you can see we just multiplied the functions, and so the domain again is the same as the previous two, all numbers x such that x does not equal negative 2 and x does not equal 1. So even when you're doing composition of functions, or you're combining functions, the domain remains the same. So it doesn't really change unless you do something that forces the denominator to change, if you will. And for letter D, the domain of f over g consists of the numbers x for which g of x does not equal 0. and that they're in the domains of both f and g. Since g of x equals 0 when x is equals 0, we exclude 0 as well as negative 2 and 1 from the domain. So the domain of f divided by g is all numbers x, such that x does not equal negative 2, x does not equal 0, and x does not equal 1. And that's the end of 3.1. Thank you.